Hello friends, in the last lecture we have studied about how to find out electric field intensity at a point due to a dipole. The point may be on its axial line or on its equatorial line. What if the point is neither on the axial line and nor on the equatorial line? Then how to find out electric field intensity at any point? So this we'll study in this lecture. So we'll find out electric field intensity at any point due to a short dipole. Now I have considered a small point K and I need to find out the intensity of electric field at this point K due to this small dipole AB whose center is O and the length of the dipole is very short. At point A minus Q charge is over there. At point B plus Q charge over is there, and as we know the direction of dipole moment is from negative to positive, which I have drawn over here as you can see in the diagram. Now how to find out the intensity of electric field at point K? So first I will draw a line which should pass through the center of the dipole. As you can see, I have drawn a dotted line which passes to the center of the dipole, and this line makes an angle of theta with the dipole. It is making an angle of theta with the dipole. Now the dipole moment of the dipole AB is P. As P is a vector quantity, we can find out its rectangular components, that is cos component and sine component. If the angle theta is over here, I can say this line, or this will be the cos component of the moment of the dipole or dipole moment. So I can write it as P cos theta, and this will be its direction. Similarly, this line, it will indicate sine component. So I can write over here P sine theta. So I have divided dipole moment into its cos component and its sine component. Since the angle theta is over here, this line will be P cos theta and this line will be P sine theta. Now let us assume that there is a dipole A1 B1 whose dipole moment is P cos theta. It can be assumed that it is a dipole A1 B1 whose dipole moment is P cos theta. So as you can see in the diagram clearly that this point K is on the axial line of this dipole A1 B1 whose dipole moment is P cos theta. This point K is on the axial line of dipole A1 B1 whose dipole moment is P cos theta. So this point line on the axial line. Similarly, if I tilt the diagram a bit, here A2B2 can be considered another dipole whose dipole moment is P sine theta, and as you can see this point K now lies on the equatorial line of the dipole A2B2. It is clear over here that A2B2 is another dipole whose dipole moment is given by P sine theta, and this point K now lies on the equatorial line of the dipole A2B2. Now let us consider that the distance of this point K from O is taken to be R. I have considered the distance of point K where I need to find out the electric field intensity, and it is at a distance of R from the center of the initial dipole, which is AB. So I have written over here, consider a point K which is at a distance of R from the center of dipole, initial dipole AP, such that KOB is theta. Now I have resolved dipole moment into its rectangular component P cos theta along A1 B1 and P sine theta along A2 B2. Now you must note this, in axial case the electric field intensity is along P. This we have discussed in the earlier lecture. Suppose if this is your dipole and we have found out that at any point, let's say at any point over here, the electric field intensity is toward the direction of dipole moment. This we have discussed in earlier lecture. Similarly, in case of equatorial, the electric field intensity is opposite to the dipole moment direction. Even this we have discussed in earlier lecture, that let's say minus q plus q is a dipole, and if this is the direction of dipole moment, we found out experimentally as well as mathematically that the direction of electric field intensity is in this direction. This we have discussed in the earlier lecture. We have derived this. So what we need to remember is, in axial case, the electric field intensity is along the direction of dipole moment, and in equatorial case, the direction of electric field intensity is opposite to the direction of dipole moment. This you must remember. This concept I have applied in this given diagram. As you can see, the point K was on the axial line of A1 B1. So the direction intensity of electric field will be along KL, that is along the dipole moment. And in second case, over here, as the point is on the equatorial line, so the intensity or the direction intensity electric field will be opposite to P sin theta, that is along Km. So as you can see in this diagram, KL will denote the intensity of electric field due to this dipole, and Km will denote the electric field intensity due to this dipole. As electric field intensity is a vector quantity, we can find out the net electric field intensity, which will be given by Kn. Now we need to find out this Kn. Now let's find out. For dipole A1 B1, as we know that the intensity of electric field is given by 2p cos theta upon 4 pi epsilon naught r cube. Mind this, we are finding this for a short dipole. So we have written 2p cos theta. Why p cos theta? Because in this diagram, the dipole moment of A1 B1 was p cos theta. So instead of 2p upon 4 pi epsilon naught r cube, I have written 2p cos theta upon 4 pi epsilon naught r cube. Similarly, for a second dipole A2 B2, we'll use the equatorial formula. Equatorial formula is p upon 4 pi epsilon naught r cube. But since for dipole A2 B2, the dipole moment is p sin theta, for A2 B2 p sin theta, so it will become p sin theta 4 pi epsilon naught r cube. Now in the diagram, as we have seen that the electric field intensity due to axial, this A1 B1 was KL, and due to A2 B2 it is Km, and both of them are perpendicular to each other. So how will we find out E net? So it will be equal to under root E1 square plus E2 square. On solving, this is the solution. As you can see, I have taken out P 4 pi epsilon naught r cube outside the under root. Inside it will be 4 cos square theta plus sin square theta. Now I can write 4 cos square theta as 3 cos square theta plus cos square theta. Now what is cos square theta plus sin square theta? It is equal to 1. So I will finally get P upon 4 pi epsilon naught r cube into under root of 3 cos square theta plus 1. This is a formula for finding out electric field intensity at any point due to a short dipole. Now what will be its direction? So direction, we use tan alpha. As I have drawn in the diagram, the direction, this is the net electric field Kn, its direction is alpha with KL. So tan alpha will be equal to ln upon KL, ln upon KL, and as we know ln is equal to Km, so I have written Km upon Lm. Finally putting the formula values, I get tan alpha is equal to half tan theta. So by using this formula, I can find out electric field intensity at any point due to a short dipole, and its direction will be given by tan alpha is equal to half tan theta. Now we'll study the effects on an electric dipole when it is kept in a uniform two-dimensional electric field. This is an external electric field in which we have kept a dipole. What will be the effects on a dipole we are going to study in this topic. As you can see, these dotted lines indicates an external electric field whose intensity is given by E. I have kept a dipole such that the center of dipole makes an angle of theta with the direction of external electric field. The length of the dipole is 2a. There are 2 point charges plus q and minus q and plus q at point A and B respectively. As minus q and plus q are point charges, if these point charges are kept in an external electric field, obviously some force will be acting on them. So on force on minus q will be equal to minus QE, and it will be in the direction opposite to the direction of external electric field. Similarly, the force on plus q will be F is equal to QE, and it will be along the direction of external electric field. Now as you can see, the net force acting on the dipole has to be 0, as the two equal and opposite forces are acting. But since they are not acting at the same point, so it will create a moment, or you can say it will create a torque which will try to rotate this dipole. Since two forces are acting at two different points, it will create a torque in this direction which will try to rotate the dipole. The prime purpose of the torque is to align this dipole along the direction of external electric field. So this will cause a torque, these two forces, and it will try to align the electric dipole along the direction of external electric field. Now how to find out this torque? So I have written force on minus q is F is equal to minus q in opposite direction of intensity electric field. Force on plus q, F is equal to QE in same direction of external electric field, which I have already discussed. Now as I have discussed, the forces are unlike, equal and parallel, acting at two different points. Hence it will create a torque which tends to align the dipole along the external electric field. Now how to find out this torque? So what we'll do is we'll draw a perpendicular AC on this line BC. So AC is perpendicular to BC. This will behave as the arm of the couple. As we know, torque is given by force into arm of couple. So either force, as both the forces are same, will take F into arm of couple, it is AC. From this triangle ABC, we can find out AC, which will be equal to AB sin theta. So AC is equal to AB sin theta. So we'll write F into AB sin theta. Now as we know, F is equal to QE. I'm not taking the negative sign. I'm just writing its magnitude. F is equal to QE, and AB is equal to 2A. That is the length of the dipole. So AB is equal to 2A sin theta. Now we know dipole moment is given by Q into 2A. So instead of writing Q into 2A, I write P E sin theta. Now what will be P E sin theta? It will be equal to P vector cross E vector. So torque will be given by P E sin theta, or P vector, that is dipole moment, cross intensity of electric field. Now this will be the magnitude of the torque acting on the dipole kept in an external electric field. How to find out its direction? Then its direction is given by right hand screw rule, which you have studied in class 11th. Now we'll study about equilibrium. There are two kinds of equilibrium: stable equilibrium and unstable equilibrium. Talking about stable equilibrium, as we have seen in the diagram, in this diagram, AB, a dipole, is aligned in such a way that at point A there is minus q charge, and at point B there is plus q charge. So the torque will try to rotate this dipole such that the dipole aligns in the direction of electric field, or you can say the direction of its dipole moment and that of external electric field is same. It will align it in such a way. I'll draw a small diagram for you. Let's say this is the external electric field. The torque will rotate the dipole in such a way that minus q will be over here and plus q. So the direction of dipole moment will be in this direction. It means the direction of external field and direction of dipole moment are same. That is, the angle between them is 0. If such a case arises, then it is known as stable equilibrium. In this, the angle is 0. In the given condition, torque tries to align the dipole along electric field. In such case, the dipole will be in stable equilibrium. What about unstable equilibrium? Unstable equilibrium will arise when, in this diagram, the dipole is aligned in the opposite manner. Means at this point it will be B and at this point it will be A. So if I draw like this, let's say this is B plus Q and it is A minus Q. The electric field is in the same direction. The force acting on this will be in the upward direction and the force acting on this will be in the downward direction. In this case, the dipole will rotate in the clockwise direction and the alignment of its dipole moment and electric field will be opposite to each other. If it will rotate in this direction, the electric field is in this direction and the dipole moment will now become in this direction. It means the direction of electric field intensity and dipole moment are opposite to each other. If such a case arises, then the dipole is in unstable equilibrium. Stable equilibrium, when the direction of electric field intensity and the direction of dipole moment are same. Unstable equilibrium, when the direction of intensity of electric field and the direction of dipole moment are opposite to each other. It means in the first case the theta must be equal to 0, whereas in the second case the theta must be equal to 180 degree. What if the dipole moment is kept in a non-uniform electric field? Till now we have studied that the dipole moment is kept in a uniform electric field. What if the electric field is non-uniform? In this case, let us study if the field is increasing along P. It means the dipole moment is kept in such a way, and in this way, this is the direction of dipole moment and this is the direction of electric field, but the electric field is increasing in this direction. It means over here the intensity of electric field is less and over here the intensity of electric field is more. So minus Q will observe a lesser force as compared to plus Q. Reason being, at this point intensity of electric field is less, whereas the intensity of electric field at this point is more, as the electric field is non-uniform and it is increasing along the direction of dipole moment. What if it is decreasing? Decreasing means the intensity of electric field at this point is more as compared to this point. So obviously minus Q will observe a greater force as compared to plus Q. These condition arises only when the electric dipole is in non-uniform electric field. Else, in case of uniform electric field, we will study stable unstable equilibrium and the torque, which is given by cross product of dipole moment and intensity of electric field. Next, we are going to learn or study Gauss theorem. It is a very important topic in electrostatic. Gauss theorem. Now what basically is Gauss theorem? Simple language में अगर Gauss theorem समझना हो तो Gauss theorem क्या करता है, वो सिर्फ गिफ्ट की पैकिंग देख के बता सकता है अंदर गिफ्ट क्या है. फॉर एग्जांपल कोई आपका फ्रेंड आपको कोई गिफ्ट दे रहा है, उसने बहुत सुंदर से उसको पैक कर रखा है और अंदर एक पेन है, तो गाउस थ्योरम क्या करेगा, सिर्फ पैकिंग देख के, बाहर की पैकेजिंग देख के बोल देगा कि अंदर पेन है. ये सिंपल लैंग्वेज में गाउस थ्योरम समझना चाहे तो ये गाउस थ्योरम है. अब इसको इलेक्ट्रोस्टैटिक फॉर्म में समझते हैं. तो इलेक्ट्रोस्टैटिक फॉर्म में गाउस थ्योरम can help us in finding out the net charge enclosed in a body by just calculating the amount of electric flux. इलेक्ट्रिक फ्लक्स कितना बाहर आ रहा है उसको कैलकुलेट करके हम अंदर चार्ज एनक्लोज कितना है वो पता कर सकते हैं. दिस इज द सिंपलेस्ट वे ऑफ अंडरस्टैंडिंग गाउस थ्योरम. नाउ लेट्स गेट बैक टू द स्टेटमेंट. The statement of Gauss theorem says that the surface integral of electrostatic field produced by any source over any closed surface. इस पूरे का सिंपल लैंग्वेज मतलब क्या है, टोटल फ्लक्स ओवर द क्लोज सरफेस इज 1 by epsilon naught times the total charge enclosed inside a surface. See, you have studied electric flux. Electric flux is given by E dot A, means intensity of electric field एंड एरिया, उन दोनों का डॉट प्रोडक्ट से हमें मिलता है आपका इलेक्ट्रिक फ्लक्स विच इज़ अ स्केलर क्वांटिटी. वो तब यूज होगा व्हेन द एरिया इज कांस्टेंट और वी नो द टोटल एरिया. व्हाट इफ द शेप ऑफ अ कंडक्टर इज नॉट परफेक्ट. कोई भी आर्बिट्रेरी इस शेप का अगर आपका कोई ऑब्जेक्ट है, अब हमें टोटल फ्लक्स निकालना है, देन व्हाट विल डू इज विल टेक अ स्मॉल एरिया, we'll find the electric flux over it and then we'll integrate it. Let's say this area is ds, then phi will be given by E dot ds d phi. अब टोटल का फ्लक्स निकालना, then we'll integrate d phi which will be equal to E dot ds का इंटीग्रेशन. So यहाँ पे वही चीज़ अप्लाई करेंगे तो फ्लक्स विल बी इक्वल टू इंटीग्रेशन ऑफ ई डॉट डी एस, एज वी नो ई इंटू ए. डी एस टोटल इंटीग्रेट करेंगे तो सरफेस का पूरा एरिया मिल जाएगा. मैं फिर बोलूँगा, फ्लक्स इज इक्वल टू ई डॉट डी एस. डी एस कोई भी छोटा सा एरिया लिया है, जब उसको इंटीग्रेट करेंगे तो टोटल पूरा एरिया मिल जाएगा. तो फ्लक्स इज इक्वल टू ई डॉट डी एस इज इक्वल टू क्यू अपॉन एप्सिलॉन नॉट, वेयर क्यू इज द टोटल चार्ज enclosed in the surface. So just by finding out the flux, we can find out the net charge enclosed in the surface. This is Gauss theorem. So Gauss theorem says that the surface integral of electrostatic field, that is E dot ds, which is equal to the electric flux, is equal to Q upon epsilon naught. Q is the charge enclosed in the surface. So to find out the net charge enclosed in the surface, we can find out by using flux, and flux is equal to Q upon epsilon naught. This is your Gauss theorem. How to prove this mathematically? For its proof, we are using a spherically symmetric surface. This proof is valid only for spherically symmetric surface. How to do it? Let's say there is a surface or a sphere whose radius is r. We kept a charge plus q at its center. Now we have taken a small area element around point P, which is given by ds. Now as the charge is positive, its electric field will be vertically outward, which is given by plus E vector, and the unit vector along it is taken as r cap. Now since this is an area, and as we know, for finding out electric flux we need an area vector. So what we will do is we'll draw a normal to it, which is given by n cap, and this will help us in finding out the area vector. A sphere whose radius is r, point charge plus q is kept at center. We have taken a point P. Around it we have assumed a small area ds, whose area vector is along the vector n cap, and the electric field due to this plus q is along this line, which is given by E vector. So moving on, we have considered an isolated charge plus q kept at the center of sphere of radius r. Now consider a small area element ds around P, whose direction is given by r vector, or n vector, not r vector, it will be n vector. Consider n vector perpendicular to ds, which will give the direction of area vector ds. Now as per the diagram, how to find out electric field intensity at point P? The electric field intensity is given by kq upon r square, so q upon 4 pi epsilon naught r square, and this r cap, here r cap indicates the direction of electric field. Now as I discussed that if we find out electric flux to a small area and integrate it, we'll be able to get the total electric flux. So the small electric flux over the area ds will be given by d phi is equal to E dot ds, as the area of that small part is ds. So putting value of E, q upon 4 pi epsilon naught r square, r cap dot n cap dot ds. As I have told you, the n cap indicates the direction of area vector. We have discussed in the diagram that this gives the area vector, and area vector, as we know, is given by n cap into a. So ds vector will be equal to n cap into ds. This I have discussed in earlier lecture. Area vector is given by a vector is equal to n cap into the magnitude of the area. So here in this case we are considering the area as ds. So ds vector will be equal to n cap dot its magnitude ds. So I have put this over here. ds vector की जगह n cap ds. Now as r cap n cap are in same direction, as per the diagram, r cap and n cap are in same direction, so their dot product will be equal to 1. So dot product will be equal to 1. So we will finally get d phi is equal to q ds upon 4 pi epsilon naught r square. This was the way of finding out electric flux along that small area around P. What if we need to find out over the complete sphere? Then we have to integrate d phi. This I have already explained. So phi will be equal to integration of d phi, and d phi is equal to q ds upon 4 pi epsilon naught r square. So I put this over here. On integration, as q 4 pi epsilon naught and r square are constant, we'll only integrate ds. And ds, integration of ds means the complete surface area of the sphere, which is equal to 4 pi r square, which is equal to 4 pi r square. So integration ds will be equal to 4 pi r square, and on solving I'll get phi is equal to q upon epsilon naught. This is the formula of Gauss theorem. Phi is equal to q upon epsilon naught, and it is also equal to E dot ds. E dot ds means E dot a, which we have already discussed. So phi is equal to E dot ds, which is further equal to q upon epsilon naught. This is the proof of Gauss theorem. Let's get a quick recap what Gauss theorem is. Gauss theorem basically says, or we can say it is basically used to find out the amount of charge enclosed in a closed surface. It should be a closed surface. So it will be equal to, how to find out that charge? So it is find out by finding out the net flux passing. So flux is equal to E dot ds is equal to q upon epsilon naught. This is Gauss theorem. Thank you, students. In the next lecture, we'll study about the application of Gauss theorem. Thank you.